Okay, we will continue today with reflection. We stopped at this point last time, and if you remember, we talked about the law of reflection. If you think of this surface here as a mirror, a reflecting surface, and you have a ray hitting the mirror at one angle, then at the point of incidence right here, you draw a line perpendicular to this surface, to the mirror, and that line becomes your normal. We call this the normal. And then the reflected ray will be going out on this other side, and the law of reflection states that the angle of incidence here, A, should be equal to the angle of reflection, B. Okay, very simple, so that it's easy to remember. Also, what the law of reflection states is that this ray here, the incident ray, the reflected ray, and the normal, those three lines, they lie on the same plane. Okay? They are on the same plane. If you think of that plane here as this thin paper, they are on that same paper, all three rays. Now, this is simple when you think of flat mirrors. You will see as we go into this class later on, into more deeper subjects. How about if you have a reflecting surface which is not flat? How about if you have a reflecting surface which is curved like this? Then, if you have an incident ray like this, how do you figure out the reflected ray? We will apply the same laws as we applied earlier, but with some differences here. Change color. If you have a curved surface, what you do at the point of incidence, you draw the tangent. So this is the tangent to that circle at the point of incidence. Then you draw the line perpendicular to the tangent at the point of incidence. That line now is your normal. Once you have established your normal, and then you have the ray, the incident ray, this is your angle of incidence. And then the angle of reflection should be on the other side with an equal angle. And that's how you figure out the angle of reflection or the reflected ray if you have a curved surface like this. Okay? And we will see more examples later on. We do have mirrors that are curved like that, and we also have mirrors. This is a convex mirror. It's curving outwards. And we also have mirrors which are concave, and they're caving in. When you have a mirror, the way we show a mirror, we show the back of the reflecting surface with dotted lines like this. So this indicates a mirror where the reflecting surface is on the outside. This is a reflective mirror where the reflective surface is in the back. The non-reflective surface is in the back, and the reflecting surface is in the caving part of the mirror. Okay? A flat mirror is drawn like this. The reflecting surface is on this side, and this is the back of the mirror. Okay? So you will have rays reflecting like that. Okay, later on, when we finish with this chapter, all of this theory, we're going to spend quite some time in this room and also downstairs to do experiments pertaining to everything that we cover in this chapter, okay, including mirrors. To give you an example, something that you will have to do later on, if we have two laser rays parallel to one another, like this, okay, they are coming in parallel from two different sources, and we would like to make these rays meet at this point. There's an object right there. We would like both rays to meet there and heat up that object. How can you make those rays? How can you redirect those rays to hit that point? You have to use mirrors. Okay? So that's something that we'll have to think about. You know? How do you do it? How many mirrors can you have? With one mirror, by how much can we deflect the beam? Let's answer this question first. Well, here's a ray. Here's a ray. And here's the first mirror, for example. By how much can we redirect the ray? First of all, something that we didn't mention, which is, I guess I need to mention. How about if the ray hits the mirror at 90 degrees as the normal? In other words, the angle of incidence, theta I, is equal to 0 degrees. What is the angle of reflection? How much? 0. If the ray hits the mirror at 0 degrees, which means it's on the same path as the normal, the reflected ray will be straight right back on itself. Okay? So, if the angle of incidence is 0, the angle of reflection is 0, which obeys the law of reflection. So let's choose a different color. Now let's say the angle of incidence starts increasing. It becomes, let's say, 2 degrees, and then 3 degrees, and then 4 degrees, and so forth. What's going to be happening to the angle of reflection? If it's 2 degrees, the incidence, the reflection is going to be 2 degrees. If the angle of incidence is 3, the angle of reflection is going to be 3. If the angle of incidence is 4, the angle of reflection is going to be 4. So how long or how far can we play this game? Until what? No, the degree increases as you move away from the normal. We started from 0. How much? 89. 89. You cannot go 90. If you go 90, there will be no point of incidence. Right. Okay? So, you can go have a ray very, very shallow like that, and this is almost 90 degrees, 89. Then, your reflected ray will be over here on the other side, almost parallel to the mirror. Okay? So, now the question I asked, by how much you deflect the original ray? Well, the angle of deflection is by how much you have diverted the ray from its original path. So this ray, if the mirror wasn't there, would have gone through on the other side like that. Okay? Now you have deflected it by this much. See that? In this case, it's going to be 2 degrees. Yeah. And how about this right here, which was coming originally this way? It would have gone down this way. Now the mirror deflected it by this much. So by how much? The angle of deflection is going to be this now. Okay? So the maximum angle of deflection you have would be 180 minus 2 degrees. 178. Okay? So if you need to deflect a ray more than that, what do? You have to use another mirror. And that's what you will find out later on if you end up working with optical equipment. You open up some kind of an optical system, typically a complicated laser system. It may be the size of a tabletop. You open it inside and you're going to find all kinds of mirrors, several mirrors, which intentionally they take the beam and they redirect it to make it go where it needs to go. Okay? So that's the use of mirrors. One more thing and then we'll move on to the next subject. There are 2 types of mirrors. The mirrors that we have at home are the cheap type of mirrors, and the reflective coating, if you think of this as the glass, the reflective coating is at the back side of the glass. Let's say this is 1/8 of an inch thickness. The coating is at the back, and then the ray hits here, it goes through this, and then gets reflected from the back out. Okay? Now, when it goes through the glass, it goes through some refraction, which we'll talk about today. But for now, just ignore it. Okay? So these are the cheap and expensive domestic mirrors. Now, when you go into a high quality laser system, you will find that here's the glass, and the refractive surface is on the top. And the reflective surface is nothing but a coating of silver, high quality silver, which has been polished, and it's on the top surface. As opposed to these here, these mirrors, they have a little bit of silver, and believe it or not, there is copper in the back of the consumer mirrors that we use at home. That's why if you have a mirror which is close to an area where it gets wet, it will start from here, the water that splashes will start corroding the copper, and you start seeing the edge of the mirror getting dark, black. Okay? So this is a back-coated mirrors, the inexpensive, and the good quality mirrors are front-coated. Because they're front-coated, when we go in the lab, when you touch those mirrors, you make sure that you never put your fingers and touch the front surface of the mirror. Okay? Because no matter how clean your fingers may be, you're going to leave an imprint on the front surface and will affect the way those rays reflect from it. Okay? Now the next subject we will cover is the law of refraction. Okay? It's also called Snell's law, discovered by a scientist by the last name of Snell a long time ago. And basically, if you look at this diagram right here, it shows an interface, and on the back it shows these dotted lines. Okay? In reality, if you have dotted lines, the implication is that you have a mirror, and if you have a mirror, you're not going to have a ray passing through the mirror. If the mirror wasn't there and you had a plain sheet of glass, then the ray would have gone through and gone on the other side, and actually this ray that goes through the glass and goes through on the other side inside the glass, it doesn't go straight. If you draw a straight line here, it doesn't follow this straight path of the incident ray. You will see that this ray, when it goes from the air into the glass, it will start bending towards the normal. The same normal that we drew before at the point of incidence. Continue that normal to the other side inside the glass. And then what happens when you go from a medium which is lighter than the second medium that the ray enters into, the ray will bend towards the normal. Okay, that's always the case. So if you go from air to glass, if you go from air to water, if you go from air to oil, any kind of medium which has an interface or a boundary between the two, right after it crosses that boundary, if it goes from thinner to thicker, it will bend towards the normal. Now imagine down here now that this was a piece of glass, and it's a thick piece of glass. It's much thick. So this ray will come down here at this point. Now here's another interface between glass now and air. Okay? At this second interface, we're going to have an application of Snell's law again. So let's use red. At this point of incidence, at this boundary, we draw another normal, perpendicular line. That's your normal. And then this is the incident ray. This is the angle of incidence. This ray, if the boundary wasn't here, would have gone straight this way, continue straight. But because it goes now from a thicker to a thinner medium, this ray will not go straight, will have to bend. And now, going from thicker to thinner, do you think it will bend towards the normal or away from the normal? It will be away. It's just the opposite of what happened up here. So instead of bending this way, it will bend that way. Okay? So, this is the angle of refraction. The same thing here. That theta 2, this was the angle of refraction at the air to glass interface. This is the angle of refraction at the glass to air interface. You follow me? And actually, you're going to do this in the lab too, another experiment. You will find out that this ray here and this ray here coming out, they're going to be parallel. In other words, if you continue this and you extend it, if this ray, if the piece of glass wasn't in the way and this ray had gone straight following this path, then you will find out that with the insertion of the glass here, this ray, which was incident before, has been moved in a parallel direction with the original by this much, this distance d. It has been shifted by this much distance. And all of that distance depends on the thickness of the glass and the type of glass that we use. Okay? So something simple like this is used in binoculars. Okay? You think of telescopes. You think of a spare telescope, it has an eyepiece here, an eyepiece here, and then if you own a pair of telescopes, think about the front, which collects the radiant energy. They're not straight across, they are over here, and there's some kind of an assembly or a housing that holds it together. So when you are aiming your telescope at an object, then the rays of the object are collected by the two lenses. Okay? And then somehow in here there are some optics which send those rays, and they have to bend them and bring them closer to one another, because our eyes are closer than what the collecting lenses of the telescope are. Okay? So everything that you are learning has applications in different types of optical devices and optical machinery. Okay? Okay. Now, on to another principle. This is the principle of refraction and diffraction. Okay? If I go back here, this is refraction. Refraction, when you go from one medium to another medium, thinner or thicker to thinner, you have refraction. Now, this one is the principle of diffraction. And this allows us to explain the phenomenon of having light traveling in a non-straight line. I gave you some examples last time of observing light around a corner, observing light of the sunrise or the sunset before the sun is visible, or after the sun sets and is not visible, you can still see the light. That's because of diffraction. So someone by the name of Young in England a long time ago created this experiment, which we are also going to recreate in the lab. Okay? We just have to get through all of this theory, so you have the foundation to do it in the lab. And his experiment is based on another theory that was developed by a Dutchman by the name of Huygens. And Huygens' theory states that light consists of these waves. Notice here, these are drawn as parallel. These wavefronts are drawn as parallel. You can do that if you think of the source being so far away, in the case of the sun being so many billions of miles away from the Earth. By the time these waves hit the Earth, the radius is so huge. If you take only a piece of that wave, a little section, okay? Think of, here's the sun, there is one wave, there's another wave, there's another wave. And if you go back away, very, very far away, and you examine a little section of that wave. Okay? This line here, this segment, is almost straight, and that's what you have right here. These are tiny segments of a wave from a faraway source. By the time it reaches the Earth and we examine a little segment, then these plane waves, they appear to be parallel. Okay? So, Huygens theory says that if you now have a little barrier here, you have a stop, you have a screen, and you have a small hole. The hole has to be very small, close enough to the dimensions of the wavelength of the light that you're using. So we know that red is 700 nanometers, we know that violet is 400, and in the middle, green is about 550, 530, something like that. So if you make this hole here about 1000 nanometers or 1 micrometer, you are in the ballpark of having that opening close to the wavelength of visible light. If you do that, then as these wave planes hit this barrier, and the part of the wave that will try to go through that hole right there, okay, will behave as a secondary wave now. In other words, if you look on the back side, on the other side of the screen, light is going to come out, okay, but this light which is coming out is light which is created as if there was a source of light right there in that hole. Okay? So this is a secondary source of light created at that little tiny hole, and now it creates its own waves. Okay? Everything on each one of these wave fronts, if you think of every point on that wave front, you can think of that as a secondary source of light. So Huygens says every one of these can be thought of as another secondary source of light. And all of the sources of light on each one of these wave fronts are in phase. So what Young did, he created another slit, put it in front of the first slit, and another screen, and in parallel of the previous screen, and created two slits, the same diameter as the original ones, and these two are symmetrically placed above the midpoint of those two slits. When you do that, and you do the geometry very, very carefully, make sure that you are not off, make sure that they're parallel, everything is just right, then this wave, which arrives into secondary slit 1, arrives also at the same time at secondary slit 2. And if you think of the source of secondary slit 1 that starts emanating now its own light, and the secondary source of slit 2 producing its own light, okay? So these are wave fronts produced by S1. Down here, these are wave fronts produced by S2. Because S1 and S2 are on the same wavefront, they are in phase. And because they are in phase, these secondary wavefronts are in phase. Okay? Now, this secondary wavefront will start mixing. Remember we talked about mixing of light last